Hi, my name is Staszek Pasko. I'm a principal engineer working in Alexa Speech. Alexa Speech is the part of Alexa that David was talking about just before, so the parts that process user speech and synthesize speech back and understand what the user is trying to say. And I will be talking today about what Alexa can do offline. So until very recently, the answer to this question has been not very much. So she would display a red ring and fail. However, we are changing that. As we announced just about a week ago, when there's an internet outage or your internet connectivity is spotty, so you have poor connection, we will now have a feature which is called local voice control. And this will allow you to control your devices, smart devices such as lights, plugs, switches. And if you have a connected Echo device such as the new Echo Plus or the new Echo Show, those devices have a built-in smart home hub, so they can actually control those devices, and now this functionality will also work when you are offline. Now, this feature didn't just materialize out of thin air, so we spent quite some time working on this, and I wanted to go back a bit. So we started, I think, about 2 years ago, and what we started with was what we at Amazon call the working backwards approach. So we first found what potential use cases, found what potential goals we want to serve. So we've identified that this would be a great feature to have, something that customers really wanted and would serve them. And we've identified two areas that would help the users. And first was obviously smart home. The second was in-car services. And that's called Alexa on Board. We have actually announced it a year ago on CES. Focusing on those two areas helped us identify the target platform that we will be working with. So those are relatively small CPUs. Think of something like Raspberry Pi. And those are tiny amounts of RAM when you compare it to the cloud software that we typically interact with. On the other hand, because the use cases were also limited, so we identified that, well, certain things don't make much sense when you are offline, then we could also simplify the functionality and to actually meet somewhere in the middle, so that we could have restricted vocabulary, limited features that actually serve the critical use cases and that actually provide value to the customer. A lot of what's available in the cloud necessarily requires cloud to function. So you wouldn't have the ability to query some web pages or query weather, because that's simply not available when you are offline. Now, still we did ask some questions. So we knew what generally we wanted to deliver. We knew generally what platforms we wanted to target, but we asked, what if we had more compute power? What if we had unlimited resources? What would be what the situation would look like? Would customers want to have devices like this in their homes? Well, some do. I have something similar, and I think that's very neat, but my wife doesn't think so. It's also not very popular to have a whole rack of servers, and this was actually one of the first pitches. So what if we could just install a server rack in your home and install all the software that we had in the cloud to serve whatever we wanted? But when you think about the car, that means even more crazy things, and that's probably not what you want. So this is an actual picture of one of the prototypes of a self-driving car. So since then, all that stuff has been miniaturized, but you still require a super complex computer in this car to actually have this functionality. So we thought that the customers would prefer something like this. So this is the new Echo Plus, and it's reasonably small. It looks nice, right? So we want to have integrated solutions, ones that go out of the way, ones that, though they are limited in forms of specifications, they are also within reason of the integration factor and the form factor of the usability. So how do we get there? So David mentioned in the previous talk what the stuff we have in the cloud, and we do have a lot of this technology in the cloud. We have speech processing, we have natural language understanding. So the next step after we've identified the direction was to think of what can we use. So what pieces of the technology that we already had can we use offline? And unfortunately, it's not as simple as this. So we cannot really put the cloud into a box and lock it there. As I mentioned, there's just too many things. So we wanted to have something more integrated. So this is on a high level how the cloud looks like. So the device, as in previous talk as well, talks to something which we call the Alexa voice service. Alexa voice service interprets your speech, talks to a skill does some actions, those actions cause some further interactions, and then you talk back to the device using speech. Or at least this is how the customers perceive that interaction, or the customer or devices. So this is how this looks like from a very high level. If you look a bit deeper, there are services. So we have a service which is called like orchestration service, and this service is responsible for sending messages downstream, upstream, handling various interactions between other services. We have services that do speech recognition and services that do natural language understanding. We have obviously a service that does text-to-speech, so it can actually synthesize speech on the way back, and every single skill is typically a service. And on top of those, we have services that handle machine learning. So they build the machine learning models for all those other services. In all, there is tens, hundreds maybe services that we would have to somehow port to copy this functionality to the embedded world. This sounded crazy, so it's not something that we can do. So let's start from the bottom. This is how the typical speech flow works for if you focus on just the basic components. So the example here, I'm not sure if you can see it, it's set Simon's bedroom light to 50%. And this is a fairly typical smart home utterance. And what we do is we process it through through automatic speech recognition, and that produces text. The text is let's say that this is the first best interpretation, and that first best interpretation is then interpreted through another service, or another component in this case, which we call natural language understanding. It's also a machine learning model. It interprets the input sentence and extracts information from it. So it classifies the utterance into an intent, which is, in this case, turn on appliance intent, and it assigns bits of the information that the user has provided into slots. Those are the parameters of this intent. This is pretty important, that this all of that changes the input into essentially a function invocation. So later on we can deal with skills that can all, similarly how we do externally for Alexa Skills Kit. The functions only need to interpret the intent, which is the function name, and they only need to worry about the parameters. They can generate speech, so they will generate text directly, which would be to say now set to 50%, or they can say, okay, if the skill doesn't know how to find a device named Simon Bedroom's Light, it's also the skill's responsibility to say, I can't find a device. Which device did you mean? Or disambiguate in a different way, or the answer could be simply okay. So all of that logic is within the skill. Afterwards, we still process it through text-to-speech and do speech output. So this looks much simpler, right? So we are no longer have hundreds of services. We have 4 boxes, which is a reasonable approximation of the modules that you would have to have on the device. So what we end up when we connect those together is an engine, or maybe not. just an engine, maybe something like this truck. So it's bare bones. It doesn't really look like a car or a truck, but it's something that allows us to build experiences on. So that's something that we can use to deliver all of those features that we talked about before. So we can then plug in functionality to drive smart home, functionality to drive all those car scenarios, not like this, but different cars, and deliver the experience we want. Okay, so we'll go into how we exactly achieve that compression. But first I wanted to do a small interlude. I'll be talking about a couple of interesting failures or interesting problems or whatever you want to call it, but this is certainly an interesting failure. Those stories are here to keep you awake during this presentation. And also those are actual problems that we have encountered when working on porting the Alexa functionality to embedded devices. So things that you could pop into when trying to deliver a system, embedded system of high sophistication, I don't know, high complexity. So the first thing I wanted to talk about is QNX. QNX and Android are two popular operating systems that you can encounter when talking about embedded software in the car especially. And we wanted our software to be portable to all kinds of target devices. So naturally, we chose C++ as our language. You might consider that some other languages are more portable, but the reality is a bit more complicated. So Java, for example, differs significantly between embedded and cloud world. Java on Android is not really Java, so you cannot really get code that you run in the server running on the device without huge modifications. C++, on the other hand, at least if you are coding to recent standards, you can take the same code, compile it for QNX, compile it for Android, compile it for Linux, compile it for Windows, and it will generally work. So we are back in where we should have been like 60 years ago or something, when C was designed. That was supposed to be the portable language for various kinds of systems. Now, getting back to the example, so what you do a lot when you're coding in C++, you allocate memory, and you allocate memory in various ways because you could want to map a file into memory and maybe allocate memory directly. And when we were running this code on QNX in a single-threaded way, everything worked perfectly. When we added another thread, which was part of the functionality of the same thread as the first one, and this is the point where QNX simply killed things, or not, it didn't kill things directly. Those things essentially got killed because of segmentation failures, because of errors that popped up in all various kinds of places. Now, there were some hints that we had which were about memory allocations. We didn't know at this point that this was directly caused by memory allocations, but if you got memory errors, then this is what you try to debug. So we tried debugging it, and QNX, interestingly, has a memory debugging library. You can enable it in a very simple way, and it simply tells you what the memory allocations are going on and where their code is trying to access unallocated memory, so it's perfect for diagnosing all kinds of errors. We run it with this code, and obviously we found out that there is no error. So with the debugging library, everything worked perfectly. So we came to a solution based on that, however. So what we suspected was the case, and we still suspect it's the case, is that QNX warns about using malloc and mmap together. Theoretically, that should have been fixed a long time ago, but unfortunately for us, it wasn't. And we ended up replacing the whole memory allocation library with dlmalloc. Dlmalloc, if you know Android, this is the native allocation library there. So it's not like it's something hugely custom. It's highly popular and didn't really really cause the system to run any slower. In fact, the memory allocations got also a bit faster. So good solution. However, you have to be worried about very interesting things happening on an embedded system, even if your code is working correctly. Okay, let's get back to the main story. So let's go into speech recognition. So that's the first box that we had. And speech recognition in the cloud is huge machine learning models. I'm talking gigabytes. So we didn't have that much memory. We knew that we can shrink them somehow by decreasing the vocabulary size. This wasn't enough. We came up with a couple of different directions. So the first directions were connected to where the cloud was going. So the cloud was going at this time from simple DNN models for acoustic modeling, which are called multi-layer perceptrons, to long short-term memory deep neural networks. And this was one promising direction. However, this didn't fully work out well for us. We needed to go further and used something which is called low frame rate LSTM. So this works by sending several frames of audio, doing frame stacking, and sending them in a bunch to a single neural network. So you end up running your network several times less frequently with more data, but overall it's much faster. And that was the key direction in architectural change on the acoustic side. But we did some lower level optimizations as well. So first thing was the structure of the network was changed as well. We introduced quantization. Typically when you train your neural networks for GPU use, which is how scientists like to train the models because it's fast, you use floating point numbers. So floating point numbers are at least 4 bytes per weight, and by introducing quantization, we replace those 4-byte integer, 4-byte floats or 8-byte floats, depending on how the model was built, with 16-bit and then 8-bit numbers. So what it means is we get 4 times or 8 times reduction in memory. But it's not just memory, it's also memory bandwidth, because when you are executing a neural network, every time you go from layer to layer, you have to do those matrix multiplications. So if you have 4 times less memory to work with, you also need 4 times less memory bandwidth, and on an embedded chip it's actually pretty important. There are some simpler things like reducing parameter count, so tweaking it so that it was a little bit smaller because we didn't we wanted to optimize it better. And finally, going back to lower level optimizations, our runtime for running models, we did a bunch of optimizations. I will show some examples later to how we actually multiply those matrices together. So typically when you do this, you use some pre-built math library which has their own idea about how to optimize this. It's not always super optimized, and it definitely doesn't handle quantized math. So we implemented our own generalized matrix multiplication using Neon and SSE math, which also added additional layer of optimization, and we were able to actually optimize overall our acoustic model 4 times or 8 times, just looking just from those engineering, not science related optimizations. On the other hand, there's the language component. The language component is less flexible when it comes to optimization. So you can do some optimizations, but within the same techniques that we used, we found out that reducing the vocabulary and tweaking how we constructed the background model, so the n-gram sizes, the corpus of data that we trained it on, it was possible to actually fit our memory and CPU requirements. So we got ASR. Now let's go to the second box. So natural language understanding is a bit more complex and a bit simpler in some way. So the basic way to think about it is you get text and you have to classify it into patterns. So yeah, you could do pattern matching, right? So this text is this intent, this text is this intent. So this is called exact matching, and we can do that. This gets tedious or quite hard to write in a very short time. So the next approach is FSTs. Finite state transducers allow you to build graphs which represent those patterns in a more flexible way, so you can generate multiple patterns much more flexibly. If those FSTs are deterministic, which means that there is only one translation going from the left-hand side to the outputs, they're also quite fast. So you can build a lot of grammar into an FST, and this will both have reasonable memory requirements, because you are essentially building patterns here. So your FST size is the size of the corpus that you have trained it on, which is both good and bad. So if you want to handle a huge number of utterances, it's bad. But if you only have like hundreds of thousands, then it starts to be reasonable. So it's we looked at top utterances that we wanted to handle. We were able to build some scripts to do automation, so extended to those FSTs with most common utterances that were actually used. And what was actually quite important here, FSTs allow very easy personalization. So you can take two graphs and compose them together. So you have one graph that represents overall grammar of your interactions, and have another graph which represents the names of the devices that the user has. You plug one graph into another graph, and you compose them dynamically, and you have now a personalized FST for this particular user. So you don't have to build a whole graph for every single user. This is pretty much handled out of the box with tools such as OpenFST. There are other techniques, obviously, for NLU. So other techniques than FSTs are statistical models, or later on maybe LSTM-based sequence-to-sequence models. And when we were kind of reaching the point where our FSTs were really, really good, we are also starting to notice that even this creation of those FSTs is kind of time-consuming. And it's getting more and more complex, because when you start to generate them automatically, you have to use weighted FSTs. Weighted FSTs are no longer deterministic. Non-deterministic FSTs are no longer super fast. So we came down to statistical models. And statistical models used in natural language understanding are typically max entropy or conditional random fields. Those are very simple models, but they do their job very, very well. So they allow you to either categorize a sequence of tokens into labels, or they allow you to assign a single label to the whole sequence. So this is essentially everything that you need to do natural language understanding. The problem with that was that in the cloud, we have used tools such as Mallet. Mallet is an excellent tool. It's a Java-based framework for training these kinds of models. It has lots of features to allow easy feature generation. It has lots of features to plug in different types of models in various sequences. You can do lots of things because it's Java. You can extend it in fairly unlimited way, right? However, the downside of that representation was that one, it was Java, so we needed to find something that would be similar but on device. And second was that the developers of Mallet never really focused on performance that much. So the typical use for Mallet is not models that we were dealing with. So our models grew huge. We had, again, models that were running into gigabytes. And that's a problem when you think about this on an embedded device, because again, memory. So we employed techniques that were able to shrink those models pretty significantly. You can read it about a paper published also a month ago or so. And the first thing that we have done is use quantization. Again, quantization, I talked about quantization for DNNs, but for statistical models, it's a bit different type of quantization. So it's not a static quantization when you essentially compress everything to an integer and then can manipulate on it. You need to do a bit of more dynamic quantization, but still, when you do it right, you can go from a double representation to 8 bits or even less per weight. And so both maximum entropy and conditional random fields are essentially a big matrix of weights, again, where the rows are labeled with features and the columns are labeled with output labels. So you execute them differently. So in CRF, you will use Viterbi. In Maxent, you simply do regression. So it's the contents that are important, that are essentially a matrix of weights. And with minimum quality loss. Actually, a fun point here was that after we introduced this dynamic quantization, our metrics for precision went up. So it was a bit unclear why, but it actually worked better than the unquantized models, very insignificantly. It's allowed us to reduce the matrix 8 times. That's first part of the optimization, but when you look at the whole model as it's generated, you also have those labels. So how do you get labels and features, sir? So features are particularly important because features you take from the input text. So the typical feature is like an engram. So you extract an engram at some position from the text and you use it as a feature in modeling. Scientists spend most of the time when they are building models designing those features, designing what those features should be, how they should be composed. And it's pretty typical that you would see like millions of features in a single model because of that. So what the models has to do is to recognize that you have found a feature and this feature is represented by this row in the matrix. Now, this operation is typically done through employing a dictionary. So you have your features, they map to rows, and that's simple, pretty efficient. However, if you have millions of features and when you extract just a few, you end up with a huge dictionary that is much, much bigger than any interaction that you are going to have. So we looked for potential answers and replaced the whole thing with perfect hashing. Perfect hashing works by translating those strings into hash codes, and from a single string you generate multiple hash codes. You put those bits into memory at the positions that represent to those hash codes, and depending on how many functions you have, how many inputs you have, what precision you want, and precision is important because perfect hashing is not 100% fail-safe, so you could have false positives. So when you train your perfect hash function on some corpus, it will always work perfectly for that corpus. But when you encounter a string that never has been seen by the perfect hash generator, you could still map it to something that already existed. However, you can predict what's the likelihood of that because you know how many functions you have, you know how many bits you use to represent, so you know how likely it is to find another string that would collide with something that you have. So we typically use likelihoods of something like 1/10 or 1,000th or 1/1,000,000th of a percent as a parameter for choosing how many perfect hashing functions we need. And even with like this very, very, very low likelihood of false positive, we are still able to just use like 10 or 12 bits per item. So we are going from very long string representation to something that's 8 to 10 to 16 bits, and gets rid of the whole feature table. We can do something similar for catalogs. In feature modeling, sometimes you don't want multiple strings to be represented as individual features because that complicates your model. You sometimes want to have multiple features represented as one. So you do what's called cataloging. So you have a catalog of strings that you have detected and you replace all of those strings with a single feature. And again, the same principle applies here. So we're using different techniques to represent those, including Bloom filters and dictionaries, and we switched to perfect hashing as well. Overall, the size of those models shrank 10 times. So we were, again, able to load those models into memory. On top of those changes, because we actually built a completely new inference engine for those models, we are able to play with some other things. So we are adding things like compression, support for different types of modeling. There's more to come here. And it's kind of interesting that when you focus on building stuff for a very, very embedded case, you end up with something that actually optimizes the things you use in the cloud, and we will be able to use it for our cloud models just as well as we are using it on the embedded side. It's simply that you have to kind of focus on that. Finally, the last box on our list was text-to-speech. And text-to-speech, we are using the wonderful Ivona text-to-speech engine, and that has its roots in embedded technology. So it was used in embedded devices for a long, long time before it actually went to the cloud, and it's still used in some places. I think some some bus stop stock in Ivona. And that allowed us to extract those parts that were necessary for synthesis on device, trim the voice. Ivona works by using concatenative text-to-speech. Concatenative text-to-speech uses a database of units, small chunks of audio to glue them together and produce one seamless unit of text that you want to synthesize. And the key scaling factor here is the number of units you have. So if you have a database of gigabytes, you have more flexibility in the things you can see, you can say more nicely, or the things that you can do. On top of that, we had some cloud features like support for long-form reading, ebooks and news, which we were not going to use on the embedded device, so we simply could disable them. This allowed us to get a very, very small tuned version of text-to-speech engine, and that engine without more modification was everything that we needed. So we got all those 3 boxes. In between those 3, all of those resources, when you port them to embedded world, you have to deal with a couple of issues, like you are using libraries. You are using C++ libraries, so there will be some dependencies that you have to use. Those dependencies can sometimes be huge, so you have to be careful about how to port them, how to embed them, how to configure them, and sometimes you have to trim their resource use. So you end up working on third-party code, which you have to fix or optimize or make more efficient. But overall, it's more of an integration work, so a bit more boring, so I'm not going to talk about this here, except for one interesting thing that we have run off. So again, checking that you are still not asleep. We found this failure along the way when we were working on Android. So this is directly connected to loading native libraries, and there are very confusing guidelines as to what should you do when you are building your applications for Android when you want to use them natively. If all that you are doing is building a Java package and it has a small native library that delegates some functionality there, then you should typically be fine. So you use your dependencies from Android world, and underneath you have just like numeric library or just some computation library or some graphics library, and it does all that works. If you want to do more things in the native world, so what we wanted to do, you end up with more interesting challenges. So if you, for example, want to link OpenSSL, well, you have to link native OpenSSL. Now, this is actually quite interesting for Android, because the system provides some OpenSSL version that it uses, and depending on which version of Android you are running on, this version could be different. And typically it's fine, so version difference here, version difference here. So for Android 6.0 and later, they changed into boring SSL. Now, boring SSL is something completely different from OpenSSL, and internally the implementation is different. And if you are using your native code to link to OpenSSL and then replace that with boring SSL, you will fail. There are some guidelines around that as well. So Android developers are nice enough to point that, well, you could try linking your whole library statically, or you could try not using OpenSSL, or you could try, I don't know, maybe renaming the whole library, or all the symbols inside it, and all the symbols that you use from OpenSSL, and do this for all your transitive dependencies. So you end up with tons of hacks across all of your code to serve this particular issue. The other approach was to, for example, package a single version for every single target Android version. So when building for Android 5, we would link OpenSSL. When building for Android 6, we would use Boring SSL. We used that approach for a very short while. It was working, but we weren't sure that it would actually work. So what we ended up with was essentially moving our whole native stack out of the main launcher and launching it separately. The reason why it failed is actually quite different, quite interesting, because underneath Android is still Linux. Android is still using Linux Linker. Linux Linker doesn't like you to load multiple versions of the library in into the same process space, and when you are running with native libraries on Linux, this is fine, because when you execute a process, you actually wipe the whole process space and you load your own native libraries. On Android, you are launching Java applications, and Java applications run in JVM, and that JVM is cloned, it's not replaced, and it's cloned for all good reasons. So its performance, that it has to have its dependencies, it has to have a lot of shared stuff that's shared between Android processes. But what it means is, if the goat loaded some versions of OpenSSL previously, then you end up using that version. And this also applies for other libraries that may be present in the system, and you will never know until you run it, because another thing that the system is doing is the problem is not really even at the level of library, it's at the level of a symbol name. So if there exists a symbol name that was loaded previously from some library, and you end up using a similar symbol, the same symbol name, and you think you are safe, it will actually break. Okay, back to the main track. We have the bits and pieces that we wanted to build this core processing. We have optimized it to actually work on the embedded device, and so we have this engine, but it's not connected to anything. So how do we put this into a system? Well, this is a simplified layout of what we have on the Alexa device. So the stuff that we have on the left is how it looks in a very simplified version today. So the stuff that runs the user interactions is called the speech user interface. It has an AVS client which talks to the cloud. So what we did, we injected a proxy or a proxy-like thing into this AVS client that allows to do two things. So first thing is that whenever speech is sent to the cloud, it's also sent to our service on the device. The second thing that it does is interfaces with the execution controller portion of our engine, and that execution controller is able to make decisions about which response to load, or when to send the request where, or if you apply any kind of logic to prioritization of responses, that can also land there. So actually, this picture doesn't do justice, but the execution controller is probably the most complex part of this whole on-device system that we built in terms of business logic, because it has to handle all of those different scenarios where different directives are coming from the cloud, different things are being processed locally, and it has to reconcile all those things at the same time, at all times. Now, what it allows us to do is to modify the cloud architecture to follow a slightly different process than what happens when you are online only. So the client, or the client software, or if you're building this device, it's essentially the same interface applies to you when talking to the cloud, or when talking to the cloud enhanced with the local engine. You don't know whether you are talking there or talking to the local thing. It's the proxy's job that can direct those responses and sends them back to your application. The controller processes the request locally. It does all the things that the engine in the cloud does. So it handles all the steps of the process. It handles all of the steps of the business logic that's around the selection of skills, interfacing with the skills, and synthesizer, when used, it uses actually a very similar response to what the cloud would send down. Similarly for the skills, so we have a skill running on the device, which is actually running an interface that is the same as Alexa Skills Kit in the cloud. So we talk to the skills through a very similar API, which allows us to use the same kind of thinking when considering what the skill can do and what the skill can be informed of. So the requests that we send to the skill are the same as in the cloud. The responses that are coming back are the same as in this cloud. This allows us, on the other on the engine side, to have very similar reasoning about what to do with those responses, how to transform them into the form that the client expects, and how to control which version to use. Internally, when you look at the orchestration and how it works, it's same process. However, we do some small modifications. So we process speech and turn it into text. We turn the text into an intent. We use local entity resolution to figure out what devices do you have locally, how to handle them, well, whether they exist or not, and then we wait, or we can wait to execute. So in the cloud, typically things happen asynchronously. You don't have to do any of this, but we have to deal with a situation when something will actually happen in the cloud and we didn't know about it. So this complexity, there is a bit more complexity here for scheduling, but when we do know that the cloud is not going to respond, then we select that local response, resume processing, synthesize the response, go through text-to-speech, everything is ready. When you think about it, now going back to this first slide when I said there is 200 of services, now it gives us a bit more flexibility in terms of what we can do because we are running on a single device. So now some things that are complex in the cloud start to be simpler. So we, even though the skills are external and accessed through ASK, they are still on the same device, so talking to them is just a few milliseconds at best, at worst, probably. And that's far less than in the cloud. So in the cloud, each interaction between services, it's several milliseconds. So we can do a lot more talking between those components, and this in turn allows us to simplify the process. So going backwards to what I was saying about NLU and how we process natural language, just the engine is slightly not enough to handle, you don't typically run the single model, you have to consider multiple things, but because we are running on a single device, we can make broader assumptions about what's happening. And for example, we don't need to parallelize all execution because we don't have so much processing power. We can do things sequentially and figure out whether they work much faster than the cloud would. So when you look at the NLU pipeline, so this is like complementary to the one of the previous slides. What happens in the NLU box, it's more complex than just those two models that I've already talked about. It's both those models and the finite patterns, which are still FSTs. But we have multiple different models, so multiple models for a single device. And we have to process some of them, select the best response, and then that best response is processed through entity resolution. So we look at, okay, we found out that there is the Simon's bedroom light. Is it an entity? Do we know about it? So model only told us that this is something that may be a name, so we now have to find what name it is. So that's the role of entity resolution, and that's how we do personalization on the device. So even though you are offline, you will still have personalized device name, personalized data, and we use cloud integration to get information about what should be in those catalogs. So when you are offline, the device still knows how to talk to your devices, and with that, it's essentially we have a complete system for doing this basic thing. So we went from speech to text through all of those systems, integrated it together. It actually works. You will be able to test it on a device when you get new Echo Plus starting a month from now or something. They should be available. And I wanted to, however, talk a bit more to finish about another interesting challenge that we had. And I earlier mentioned that we did all of those deep neural network optimizations. And this is going to go a bit into that. So this is a function that does integer sum essentially with saturation. So when you are multiplying integer represented matrices together, matrix multiplication works by multiplying vectors, and then intermediate products get summed, and those sums go into the result. However, when you are working with float representation, you have flexibility. So when you go out of range, you simply shift the floating point. If you're working with integers, when you go out of range, then you have overflow. If you have overflow, then you have to do something about it. Either you can ignore it, and that's a valid approach. We've used it on some platforms, or you can do this. And this essentially takes two integers, checks whether their sum would be above the limit for what can be represented in a 32-bit integer. And if it is, it's going to replace it with either a maximum or minimum integer. And this code here is actually pretty efficient when you consider this process alone. So this is one of the more optimal ways that you can do it. So there is a bit of bitwise manipulation magic here that's happening between those numbers that we process, but without looking deeper into that, this allows us to do just a couple of instructions to return the correct results. However, there is branching here, and when we looked at our profiles for when we were executing those models, this function was the most heavy frame that we had in our whole profile. So, and I mean like by far, so it was representing more than half of our CPU. So it was a bit silly, so we wanted to optimize it. And optimizations that we had started with something like this. So we are going into assembly here. This is ARM processor assembly, and does anybody here know what this is or understand this? A couple of people. That's very good. I didn't expect that. So there is to explain what happens here. When you write in native C code, you can go even deeper and execute assembly code, and you can do this by introducing those ASM constructs, which inform the compiler that you will be taking some inputs, map them into things that assembly knows about, and then run those instructions, essentially as you put them here. And the instructions that are happening here is essentially we are loading 4 integers at a time, so major optimizations here. We are taking 4 numbers at the same time, and we are using the low-level qadd instruction, and this is the feature of the ARM processor that it actually has a dedicated instruction for saturated additions. So they thought about this, they exposed this functionality to the user. However, if you are programming in C, then, well, there is no way that you can tell directly the compiler that you want this to happen other than something like that. So we did that, and we loaded it from memory into those registers, added 4 numbers together, stored them back out into memory. Everything is nice. However, there are 2 things that didn't go well. So this improved our performance, but it improved our performance only very slightly. So it actually cut down a lot of compute, but improved things like 20 or 25%. Weird, right? So we eliminated lots of this like bitwise manipulation and so on. So there are 2 things that are wrong about this code that we have identified through lots of work on, like, probably the most expensive lines of code that I've ever worked on. So just to calculate the time. So first thing is that this code loads everything from memory. So when you are writing chunks like that, you have a choice. How do you process input or output? But when you load everything from memory, then you essentially tell the compiler that you don't know anything about what will happen. And another thing that happens here is that it hurts inlining. So if you wanted to inline this function, but you would want to inline this function, but you're effectively writing it in a way which forces the compiler to load the intermediate parameters into memory before they're actually passed to you. So if this gets injected into the after the already optimized way that we were multiplying integers together, the outputs which were in an integer were in an register had to be loaded from the register to the memory, from the memory into this function, and out of the memory returned from this function back into a register, which is again expensive and prevents and makes inlining hard. The second thing that's hurting here is the assembly block itself. So compilers nowadays do a lot of low-level optimizations, and those optimizations are in large way involved with reordering of the operations. And this all works while the compiler has full control over the code. If you do anything like this, the compiler will simply give up. So anything that happens before this assembly block inside a single execution unit will have to complete before this assembly completes. And this means that if there are any intermediate computations and so on, all of those have to complete as well. Anything that's computed here cannot interleave with anything that happens after this block. So in a way, we were helping the execution, but hurting the compiler. So what could we do about this? So there are actually two different things. It's not working. Okay, so more assembly. And there are two things. The first approach that actually optimized this process alone about 3 to 4 times, and the overall matrix multiplication was again optimized by another 30%, is this first assembly block here. And this assembly is working a bit differently. So first, it doesn't require to it integrates with memory, but in a different way that we loaded before. So it loads the immediate parameters into registers, and it kind of knows that the function code around it was working with a memory block. So it produces the outputs into some memory, and now this will run on this memory. So it makes more assumptions about where it will be placed in code. Second thing is we are no longer using several instructions to do well, we are using some qadd instructions. However, there are just two, and there are just two because we used another vector instruction. So the outputs from the previous steps were actually optimized vector processing, because there are vector functions that can allow you to multiply things in parallel. We used that before. The saturated additions on 32-bit ARM do not have a vector function that goes from vector representation to scalar representation for saturated integers. So this way that we did it here, we prevented this conversion from vector to scalar to happen too early. So we actually assume that the representation will be vectors. We use a function that does some vector processing and then loads the outputs into registers, and then we work on registers alone. So that was one thing. The second thing was because the still throws out of execution or out of order execution, we thought about how to do it better. And actually, we have another function which is not here because it's essentially a single line of code, which is so that's essentially highlighted here, the vq_add s32. That's the C function. I will talk about it in a minute. So we are using this to sum up blocks of 4 integers together, and then at the very end of a single vector, we are using this function only once. So we now have full out-of-order execution for the whole vector, and only degrade into this block once. This actually saved a lot of memory. However, you can do it even better on 64-bit ARM, because it has vector to scalar intrinsics, and this is how this code actually looks like in other places. So you don't write an assembly code, but you tell the compiler to write vector-based assembly code for you with functions that are called intrinsics. And those intrinsics map one-to-one from the C code, like this VQADD is vector saturated addition for four integer number. Well, two is the result, but it gets input is 4 integers, the output is 2 integers, and then we copy them together. What's interesting here is that those functions like vgetLane, they don't actually generate functions. It's syntactic sugar for the compiler to know where to get data from. So this actually generates free assembly instructions and does the same work as we have in 6 here and doesn't break out of order execution at all, because the compiler now knows what functions produce what results. Okay, and with that interesting side story, it's time to end our journey into offline Alexa. I hope you enjoyed it. I hope that was useful. If you want to chat, I'll be here later on, and we'll be switching to the next speaker.
Thank you, Staszek.
Thank you.